Hello, everyone. Thank you once again for attending this presentation. The title of this paper is called Transformers in Time Series Forecasting. We want to do a brief transfer learning performance analysis. So the work is done, it's part of my PhD research and done under the supervision of Professor Kyamakya. I'm from the Klagenfurt University in Austria. And together are my team member in the research group. Yeah, so this is the outline of this paper. I will start by again giving the background and motivation for the research, and then I will define the problem statement and research question for this work. We'll go together through the state of the art of transformer, first of all in time series forecasting, but also in time series pre-trained models. And then we'll show the models that are used in these experiments and some transfer learning techniques and experiments and results discussion will be given and a research contribution, and we'll end with some concluding remarks. So time series are almost everywhere. And now here, long-term forecasting is very much needed in some application. Long-term forecasting, forecasting where you need to focus to go further in the future. And in long-term forecasting, also have the aspect or the problem of long-term dependency. So we see that there is a dependency of values in a kind of long term. And we need to have models that can do better in these types of works. Fortunately, transformer-based models have emerged as powerful models for time series long-term forecasting. But again, the transformers did not start in time series. The use of transformers started in natural language processing and computer vision. Now we are talking about ChatGPT. That is, it's based on the transformer architecture. So transformers are well advanced in natural language processing and also in computer vision. Now they are starting to be used in time series forecasting. Again, because I will touch on the aspect of transfer learning. Sure, insufficient amount of data, it's a problem. It's a challenge in deep learning. So transfer learning with transformers are being exploited. As I'm indicated in natural language processing, we've got a solution like BERT or GPT that have existed. But pre-trained transformers for time series forecasting is an area that is not yet explored. All right. So, and in this paper, we aim to investigate how pre-trained transformers can be effectively utilized and fine-tuned to improve accuracy and efficiency in time series forecasting. So this picture here just give us the context of time series, of transfer learning with the idea of the source domain and the target domain, and where the learnings performed from the source model to the target model. This is how we define a problem statement. There is a need for extensive studies and experiment aiming at developing pre-trained transformer models for different tasks in time series forecasting. And the research question that we have here, what is the current state of transformer models in time series forecasting on one side, and what's the state of the art of pre-trained models, pre-trained transformer model of in the field of time series? We will approach the state of the art in those two ways. Research question 2, which techniques can be used to perform transfer learning performance analysis for transformer model used for time series forecasting? And as a research question 3, how does the transfer learning performance of transformer-based models compare to shallow neural networks for time series forecasting with respect to the transfer learning gain? All right. Transformers models have been used a lot in natural language processing and in computer vision, but now researchers are modifying the architecture of the original transformer to fit the time series data. And some of the well-known transformers for time series, we've got the log trans, we've got the informer, we've got the autoformer, we've got the piraformer, we've got the fedformer, and lately the conformer that have been designed. And again, papers, there are a lot of papers that can give us more details about these transformers. And when it comes now to transfer learning of transformer models for time series, again, it's an unexplored area, as I indicated. But by surveying literature, we came across two pretrained transformer models. One is called traffic BERT, another one called tab BERT. So traffic BERT, we can see BERT, which is a pretrained model known for natural language processing. Obviously, it's been modified to suit time series data, the same way as tab BERT. Okay, so eventually, literature emphasizes this. Actually, again, it comes from a survey paper, a recent 2012 or 2023 survey paper that suggests that future research on time series pre-trained models should concentrate on suitable transformer-based pre-trained techniques for time series forecasting and anomaly detection. And we then want to do some, we call it brief transfer learning performance analysis, because we will use these models, the conformer, which is one of the transformer that has been designed for time series. We've got also the vanilla transformer. So also vanilla transformer is, it's just the initial transform, but where the upper part that does either language translation or language classification, that part is changed so that it can do time series forecasting. But also we want to compare to the LHCM and MLP. So this how the architecture of the conformer looks like. This how the architecture of the vanilla transformer looks like. And obviously you are familiar with the LSTM. So, one colleague presents largely on the LSTM yesterday. And this is how the MLP look like. And we want to compare how these architecture will perform, first of all, time series forecasting, and also with respect to initial experiments for transfer learning. The transfer learning techniques that we intend to use here, first one is it's referred to as feature extraction. The other one is referred to a fine tuning, and another one is we will be phrasing the whole model completely. So by feature extraction, simply put, means we take a portion of the model that we freeze after it has extract the features of eventually, and another part of the model it's used now in the target model to learn about the new model. However, the fine-tuning model, the model is trained by the source data, but now in the target data, we continue the training of the same model, similar to what we presented in the previous paper. Now, this other technique is a naive. I refer to it as naive technique because we'll freeze the whole model. A model that has been pre-trained, we freeze all the weights, and we just use it for testing in the target domain and see how it's going to perform. I can promise you the result was awful on this one because it didn't have a chance whatsoever to learn from the new environment or in the target domain. So here I'm explaining quickly what's feature extraction technique about, and I just want to give these details for the model that we used for the conformer. For the feature extraction, there is the section called the SIN, the stationary and instant recurrent network. That's the part that will be frozen, and the rest of the architecture the weight will be updated in the target domain. For the vanilla transformer, the multi-head attention of the encoder block is what will be frozen, and the rest of the weights will be updated or be used in the target domain. However, for the LSTM and MLP, once again here we used shallow MLP in shallow LSTM, means with only one hidden layer. So the part that we froze is only the weight from the input to the hidden layer, okay, and the upper part from hidden layer to the output layer, those weights could be learned again. For fine tuning, as indicated for all the models, we started training in the source model, so in the source domain, and in the target domain, we continue the training. So the training does not start from scratch. It starts, the training in the target domain starts with the weight initialized from the previous training. And the freezing the whole model trained in the source domain, and we freeze all the weights. In the target domain, we just do the testing. And because this is a long-term forecasting, uh, uh, especially for the prediction horizon, using 96 points, we're trying to predict in the future 96 point, 192 point, 384 point, 7 and 768 points. So you can really see that it's actually a long-term prediction. In the training, we're using 10 epochs with early stopping patience of 5. But for fine tuning transfer learning technique, we just use 5 epochs, and we use the Adam optimizer, loss function MSE, evaluation matrix MSE and MAE. Here we did not use we haven't used yet the matrix that we defined because this is still new territory. And here we are using 3 data sets, 2 which are benchmark dataset that are being used extensively for transformer in time series, the ECL. We also have the ETTH1 and ETTH2, but also we use the data sets that we used in our previous work to see how the model will perform also using this data set. I will not go too much detail through this, but what I can show you, when it comes to transfer learning, we simplified what we discussed in the previous paper, having different scenarios. I think you remember, but here we are considering only 2 scenarios. Okay, actually no, 3 scenarios I will say. Scenario where we are doing the training in the source domain, and another scenario where we are doing the training in the target domain, and now we are a third scenario where we are doing the transfer learning from source to the target domain. So we are not having the other 2 scenarios. Now, because, yeah, and so now we are comparing, this just to compare, okay, how much gain do we're just using the transfer learning gain, by the way. If we were to train the model in the target domain, and if we were to use transfer learning, are we gaining anything? That's the question we asked ourselves here. And we have the same setup for all the 4 models that we used: the conformer, the vanilla transformer, the LSTM, and the MLP. So these are the results for the fine-tuning technique. But what I can mention is that not talking transfer learning, talking just normal forecasting performance, it's quite interesting to see that they perform, obviously in general, the conformer perform better than the rest, and the worst are the LSTM and MLP. Surely we understand because LSTM are not fit for longer long-term forecasting. In fact, you know about problem of the vanishing gradient and exploding gradient. MLP also not set for this, but we just want to confirm that we will have the same result. The conformer transformer and vanilla transformer, they give the best result. But again, comparing the 2, in some data sets, conformer perform better, and other data set, vanilla transform perform better. But again, here we know that another difference between the 2 here is actually the computational complexity. Yeah. So these are the result of the feature extraction text transfer learning technique, almost having the same outlook of the result. We did not include the freezing of the whole model, as indicated, they were awful and it was predictable, all right? But what interests me is these two tables where we are now just expressing the transferring gain in terms of percentage, all right? So, and in most of the cases, conforma is the best gain, and again that varies according to the horizon number of value we want to predict in the future, and the result also vary actually. Fine-tuning result and feature extraction result, they really vary. And one of the future work that we give ourselves is to see how we can on one side come up with ways to fine-tune the model or to look at the architecture to see which part to freeze so that we can come up with a trend. We see obviously the conformer perform well compared to the other ones, but we still need a trend, right? That trend hasn't come up very well. So we assume that is future work. We need to look at some fine-tuning techniques and look closely on the architecture model, especially when we do feature extraction, which part of the architecture to freeze and which one not to freeze. And yeah, basically that's what we've come up as insight from this experiment. But still, the idea is surveys are adamant that we need a lot of experiment in designing pre-trained model for time series forecasting. And as I said, on this we add on top the transfer learning aspect of it. So these are early results, and we keep on doing experiments. Future conferences will come surely with new discoveries. So to conclude, this work draw the attention to transfer learning techniques applied to transformer in time series forecasting. Preliminary results reveal that there is still much that needs to be done, and we have to further explore parameters for fine-tuning adjustment and also further analysis of the transformer architecture to achieve better transfer learning gain. And there is a need of a systematic study of the transfer learning performance using transformer the transformer design model. Here, I'm trying to suggest that maybe if we can use the systematic study that we present in the previous paper to see what can come out of that. And at the end, this work just encourage further research on time series pre-trained model. Thank you very much for your attention.